Looks good. Phew. All right. Teamwork is important, as we all can see. So we have a wonderful team as well that played a big role in the organization of this workshop. I'm one of the organizers, Jun Chin. Everyone calls me TJ from Adelaide Uni. You'll hear from some of our co-organizers later. And this workshop wouldn't happen as well without an excellent group of reviewers or program committee members. These are all of them, and let's give them our appreciation as well. So I've only a few minutes to give some high-level information. One of them I'd like to share is paper statistics. This is the third iteration of AI4Space workshop. This year received maybe 30 submissions, 25 of them viable. Unviable ones were because basically they were mainly work in progress that didn't get completed before the deadline. So we have 25 viable submissions from both the workshop and the challenge. Each paper received at least 2 reviews. The reviews were conducted in double-blind manner, and decisions were made by workshop organizers. And the workshop organizers therefore act as meta reviewers on the submission system, and they have set it so that the decision makers do not know the identity of the author. So it's all double-blind. And 12 papers were accepted in total, which gives an acceptance rate of 48%. As far as I'm aware, that's maybe slightly lower than the average acceptance rate of a CVPR workshop. So I think that's a good outcome personally. And we also invited 2 papers from the main conference for poster presentation. So these 2 papers, of course, will not appear in the proceedings of CVPR workshop, but instead on the CVPR main proceedings. A rough description of the structure today. You've all seen this on the website. I guess the 2 important ones to share now is the poster session will be held in the exhibit hall. I've checked it out earlier. You have to go up the escalator to level 4, find out where the sky bridge is, and find out exhibit hall 4E and 4F. 4E and 4F. And that's where you pick up your posters as well, for those who haven't picked up yet, if you printed with CVPR. The other important one is in the award ceremony, we'll be announcing Best Papers awards as well as the Spark Challenge winners. So please stay until then if you want to know who won. Okay, spotlights. As I mentioned earlier, please walk up to the podium with your laptop, share your screen via the Zoom, and please keep your talk to 4 minutes strictly, no Q&A. The poster session is for the interactive Q&A, and we have 1 minute for changeovers. And here's how you join the Zoom. I've already mentioned that a few times before the start. And again, most of you probably wouldn't have picked up your poster yet. Ethan has very kindly agreed to go and pick up for all of us, if that's okay by you. If you want Ethan to check whether he can pick up the poster on your behalf, send your poster printing confirmation. There should be some kind of an ID number. Send it to Ethan, that's his email address, and he'll try to pick it up for you at around 10 o'clock before our poster session. Okay, so by the time you get there, hopefully the poster will be ready for you to pin to the poster board. So his email address, ethan.elms@adelaide.edu.au. He's a trustworthy person. He's just sitting right there. Ethan, just stand up and say hi to everyone. He's my student. So yeah, send him your poster ID. Sorry, the confirmation ID. So with that, let's begin the workshop. And according to the schedule, Jamila will be speaking to us about the Spark Challenge.
So welcome everyone again to the AI4Space workshop. And thanks also to TJ for hosting the Spark Challenge within this edition. So I'd like to start with a video Let me see if it works. Click, I guess it should. Yeah. So this is our promotional video that we use every year. So Spark is this year is the third edition. We already had the first one in ISIP 21 and the second one with TJ in AI4Space 2022 with ECCV. And the motivation for our challenge is to promote approaches that are data-driven for space situational awareness with applications that you saw, active debris removal, on-orbit servicing. And what is special is that we share data for everyone to use, data synthetically generated, but also data collected in our lab from the University of Luxembourg, the Zero-G lab. Let's see. And this year, I'm very happy to say we had a record participation. We had two streams. The first stream was on segmentation, satellite segmentation, and the second one on trajectory estimation. This is where we mix it up. We had synthetic data as well as data captured in the lab. Oh, lost the whole thing.
Oh, HDMI.
Ah.
Yep.
Very good. So what you see here is one of our mockups that we have in the lab and that we simulated as well. Through Unity. Okay. And this is where we have mixed type of data. If I go to the next slide, that way we move. So the challenge started early on, mid-January, I believe, and we gave a bit less than 3 months for everyone to work on the challenge. We offered also the opportunity to submit papers. So we have a couple of papers also within the proceedings of the workshop. Yeah, and today we will announce the winners. I will not do it right now. You have to stick with us. We'll announce it at the very end. Okay. So as I mentioned, we have the first stream, which is the spacecraft segmentation. We had 10 categories of targets. Here we used synthetic data with 8,400 images per category, and 80,000 were reserved for training and validation, and 4,000 left for testing. As I mentioned, we had a record participation, almost 200 submissions from for over 40 participants. And the second stream, which is very exciting for us because it gives I believe, the first challenge with this trajectory estimation, mixing synthetic and data collected from the lab. So we had 300 images per sequence, and 30, so overall 30,000 images in total, with, as I mentioned, the target Proba 2 satellite that we have as a mock-up in our lab. And we had 100 synthetic trajectories for training and validation and 4 real lab trajectories left for testing. We had 92 submissions in total from 33 participants. I'll speed up here just to mention, thank also the team participating and preparing the challenge. As you know, it's always hard work. So we have Arun Kumar, Mohammed, and Vincent, who are back in Luxembourg, but following us, I believe, online, right? And for our winners, we thank already our partner, NMO, our industrial partner, who are putting 3,000 euros for the winners that are split between the two streams and shared between the first and second winners for each stream. So we'll announce those at the very end, so stick around. Yep.
So now for our first invited talk, we have Professor Sunjo Chun from Caltech. He's the Brain Professor of Control and Dynamical Systems at Caltech. Sunjo also serves as a senior research scientist at JPL. Sunjo received his PhD from MIT, I think in 2007, and then served as faculty at UIUC before moving to Caltech. Sunjo has done amazing research and has research focused on distributed space systems, space autonomous systems, aerospace robotics, and has been one of the leading researchers in the field. What I like about his work is a good mix between theory and systems work. And he's won numerous awards to list UIUC Engineering Dean's Award, Arnold Beckman Faculty Award, Young Researcher, Young Investigator Program, NSF Career Best Paper Awards. Yeah, I mean, 3 Best Paper Awards, 5 Best Student Paper Awards, and I can keep going. I met Sunjo when he recently visited MIT and gave a talk on sort of similar topics, and that talk is now the most viewed talk on the MIT robotics seminar. So it's our great pleasure to invite him to the AI4Space workshop. So please join me in welcoming him.
Thank you so much. Yeah, so actually, my talk will be slightly different because I wanted to actually tailor to this particular community. So thank you. If you want to see more about that contraction stuff, actually, I ask you to watch that video posted on MIT robotics seminar series. But hopefully, I present something interesting to you in this computer vision community. And there is a delay, maybe because of a large amount of videos. Yeah, so very quickly, very impressive work, a lot of kind of a work, kind of trying to combine the machine learning AI with robotics. And I think what I want to mention here is that this, although AlphaGo and AlphaZero is very impressive, and with these like video games beating humans, they are kind of limited to kind of finite, like a state and action space. And also some of this work, high-speed racing is either video game or very kind of known environment of like a racing track. So what I'm actually interested in, and a lot of people actually in robotics I do, is actually unknown environments, actually outside your laboratory, and also continuous dynamics. I mean, it's not like you have playing the board game. You are talking about continuous dynamics and continuous environment. So that's actually poses unique challenge to planning and control, and for computer vision related problems, estimation theory. So that's what I'm going to talk about. So one example of the highly uncertain and disturbing dynamics and so on is that basically drone. So this is actually my prior work, and that was published in Science Robotics. You can see that my student, Michael O'Connor, is having a difficulty in holding the umbrella. So we actually generate this kind of wind disturbance, and we have this machine learning-based rapid adaptive controller that can actually handle this really challenging disturbance. So that's called the neural fly. It was published in Science Robotics in 2022. And basically, this is kind of a nice combination of a rapid adaptation using adaptive control, rigorous stability guarantees, because anyone can actually propose a new controller and then maybe show that in the laboratory, but how you can kind of scale that up and generalize it. It has a nice, I mean, as far as I know, I mean, there is no known work that can actually do like a real-time backpropagation of a gigantic neural network. This work sort of does that in the sense that you identify what the parameters of the deep neural network, multi-layer and hidden networks, and how you actually identify the last layer as the kind of things that you have to update in real time to correctly account for time-varying winds. And those winds-based disturbance is independent of state. So, I mean, typically you have a state-dependent disturbance. You can actually train the neural network. And also another thing is that it's known work. You can actually do a spectral normalization to regularize the slope of the deep neural network, and then you can actually prove the stability. So it's not really black box anymore, because at least you can guarantee that some bounded behavior out of neural network, and we can use that for stability. So why I'm talking about the drone in the computer AI4Space, because I do have a spacecraft laboratory. It's actually one of the largest flat floor in academia in the US, at least. I don't know about the other countries. So we have a big spacecraft simulator that can actually simulate the spacecraft dynamics. You can see that there are actually reaction wheels, and we have thrusters. And basically what we are doing is that between the aircraft or drones and spacecraft, we are kind of sharing a lot of autonomy hardware, sensors, and even the autonomy computer. So speaking of spacecraft, so that's the spacecraft simulator we have in the lab. So you can actually, each spacecraft can simulate a 6-dock. It's not just like a translational motion on the ground. It can actually move up and down, and also it has a spherical air bearing, so they can use reaction wheels or thrusters to control the orientation. And the one example of this project is that basically flyby maneuver with the interstellar object. Actually, we have two known such objects. The first one is the Oumuamua. So the challenge here is that you have like a really large inclination, and I mean, you think that the drones are fast and spacecraft are slow. The relative velocity between a small body like an interstellar object, basically a comet, and the spacecraft could be actually 290 times the speed of sound. So there is an immense change. You have to make a rapid decision. So one promising application of deep neural network for control is that basically you approximate the centralized optimal solution that can actually plan the trajectory, because you don't really have a maybe onboard computation to do real-time optimization that we are going to talk about actually pretty soon. What time did I start? You don't know? I think we started definitely past 9, 10. Anyway, so this is some experimental validation of our trajectory optimization, because I'm going to talk about multi spacecraft aspect. So for vision, you have a multiple spacecraft coordination of estimation problem, but this is more control problem. So we have a way to actually coordinate the collision-free, pure optimal trajectories using sequential convex optimization. And then basically you can eventually dock. And you see a lot of this kind of application. I don't know why it's called kind of slow. Spacecraft are slow in this sense, but anyway, they're kind of approaching each other and then do autonomous docking, right? You can see that. So we have an algorithm to do that. And then the next extension is just published in Transactions on Robotics, is that we can even consider the stochastic disturbance, like dynamics are perturbed by stochastic noise. And also basically, this is a computer vision problem, and you're estimating the, like, you can see it from the previous Spark challenge. You have this like uncertainty coming out of this relative navigation of your spacecraft using computer vision, and you can also incorporate that kind of stochastic noise in the chance constraint when you talk about the collision avoidance. Anyway, so we have a very competent kind of method of even incorporating the stochastic dynamics and chance constraint or probabilistic constraint, incorporating the uncertainty in terms of vision-based navigation. So you can see the slew of these trajectories kind of capturing the robust approximation of a collision-free and pure optimal trajectories of the spacecraft for like reconfiguration, autonomous long deviation docking. So I just wanted to kind of talk about these, but without any machine learning. So this new work actually is under review for Science Robotics. Is that some of this kind of structured optimization-based trajectory, because you want to do some trajectory optimization of long deviation docking, multiple spacecraft reconfiguration. They are kind of dependent on the initial conditions. So I'm going to just speed up and then show some example demonstration. This is actually Monte Carlo tree search. Obviously, you probably know that, like a multi-armed bandit problem for the machine learning community. And this is kind of a tree-based kind of search and simulation. Actually, AlphaGo and AlphaZero use MCTS with neural network-based kind of approximation of policy and value network. So we found a very nice way of handling continuous dynamics, because AlphaGo and AlphaZero is not about the dynamics, it's just Go game. So this actually use this is a DARPA project, and compared to the sequential convex programming or different sorts of MPC problem, you can actually even back up to find the best trajectory. So you have this exploration aspect as opposed to just having exploitation of kind of optimized trajectory. And we are showing that using our spacecraft simulator, potentially like kind of capturing the malfunctioning target or spacecraft using these two spacecraft and tether. So this is our experimental validation. Hopefully you find it interesting. So as I said in the title of the talk, contraction means that some stability measures. So we have a mathematical way of kind of analyzing that stability, whether you're developing the estimation method for your computer vision. So I'm talking fast and a lot of stuff. My objective of this talk is that you maybe watch this recorded video of this conference, and also maybe you look up my name and you can find some relevant papers that actually can, hopefully you can gain more understanding of this theory. So we just gave a talk, tutorial session in CDC. This is the best control theory conference, and you can find this tutorial session and videos of a contraction theory for learning-based control and estimation for computer vision. So essentially what we are trying to do is that a lot of things are not just single point, it's the trajectories. So if you are familiar with the nonlinear stability theory, you know the Lyapunov function. So the new stability theory method is called the contraction theory. It's all about the finding the stability of multiple trajectories. Why this is useful for computer vision? It's not just about control problem, because obviously for control problem, you actually have a desired trajectory, and then you actually ensure that your actual trajectory from your spacecraft is converging to this, provided that this condition is met. But it's for estimation problem or learning-based problem, you have a true dynamics and then learn the dynamics, and obviously the learning error, F true minus F learned, actually can be maybe assumed to be bounded, and provided that bounded assumption, you can actually bound the stability condition so that you can actually see that the estimation error between estimated trajectory from your observer and the actual unknown the true trajectory from your dynamics, for example, like a relative dynamics, relative state between the spacecraft can be exponentially bound, okay? So this is actually known stability result, and we are formalizing that with a global exponential stability. Okay, so a lot of math equation. Why this is useful? It's not just about continuous dynamics. You have a time dynamics, discrete time dynamics, and then you can also formalize that, and alpha is kind of an exponential rate, alpha is smaller than 1, and then you can actually see that the error, initial error between true trajectory and estimated trajectory will exponentially converge. Why this is important? People talk a lot about reinforcement learning. Every known result and theoretical result in the existing in the reinforcement learning literature are basically twofold. First one is that basically Bellman equation, basically making connection to the optimal control theory. Bellman equation is originally from the principle of optimality, optimal control theory for discretized dynamics problem. Second one is that all the stability proof of reinforcement learning is based on this contracting gamma, whether that's called the discounting factor, gamma should be smaller than 1, or learning rate still smaller than 1. That's exactly like here in discrete time dynamics of the thing, this alpha is smaller than 1. That's what you have. Everything is like that. People don't actually emphasize this. So this is all coming from the contraction kind of dynamics. And I think one thing that I can make a connection to is that everything about the proximal policy optimization and so on, you can also make a connection that this gradient basically approach coming from the maybe stochastic gradient and so on, is basically you can analyze the stability using contraction theory. So for example, the gradient descent, you can actually prove that if you have add additional assumption like L smooth, Lipschitz smooth, and also the original cost function is not just only convex and strongly convex, then you can actually prove the exponential convergence of gradient descent. I don't know if you know about that. So anyway, for more relevant to SLAM community, this is a new paper. Then we actually proven that like you can apply the factor graph optimization for large scale real-time SLAM, and then you can actually prove the exponential convergence provided under these assumptions are correct. So why I got interested in kind of machine learning, estimation problem, because if I went to the robotics conference with a computer vision related topics, everyone is almost like 20 years ago, 10 years ago, assumed that what you have to do for estimation is only extended Kalman filter or particle filter, which I didn't like. So I wanted to actually develop, because it's very easy to show that or the Kalman filter variation, extended Kalman filter, unscented Kalman filter, and whatsoever, can be actually diverged with a heavy nonlinearity in the dynamics and measurement equations. You get ton of measurement equation nonlinear in the vision problem, right? So we have some extensions of this kind of Kalman filter where you actually extend the curves as a features instead of points, and we also use the polygons to actually represent the features. So we try to extend that. This is a published paper, but we recently extended that to spacecraft examples because we have a ton of polygons on the spacecraft features. But so going back to the contraction, we can actually prove that two individual trajectories on the stochastic noise are converging, provided in this contraction condition. So what we are doing is that we design the robust filter that can outperform the extended Kalman filter. So it's robust, optimal, it will never diverge. And so this is kind of some extension of a Kalman filter extension, that almost like a nonlinear H-infinity filter that can be used for computer vision problem. Just I wanted to explain this to you, and some new extension of convexifying some of the cost functions. So it's a transactional automatic control paper. So takeaway message is that there is something better than extended Kalman filter that can actually ensure the stability and robust convergence of this your filtering estimation problem. The problem with that method is that you have to observe the convex optimization in every time instant, which is really bad sometimes. So what we are doing here is that we can also train the neural network to actually approximate some of the solution you need for this real-time convex optimization. So the newest extension is that basically we can also look into this fourth estimation. So this is a new paper basically just published in RAR. And then let's see paper. So basically you can also estimate where the fault is. And then basically you can quickly adapt to the failure estimation, which propeller actually failed. So you can kind of visualize the spacecraft thrusters. You have maybe 16 thrusters. Then you can kind of quickly kind of identify which thruster failed while you are running running the like a model, like adaptive, like a learning-based controller to a compensation of stability. So with our neural fly fault tolerance extension, we can easily see that it can account for these failures. And more relevant to this community, this is under review for transactional robotics. We got the first very good reviews. Basically, we can also apply this kind of a learning-based deep neural network compensation for now terrain. And then what we are doing is that we actually use the visual foundation model, like a Dino V2, to actually train the neural network that can actually generate the friction model. I thought that as a person working on drone, I thought that the aerodynamics is the biggest challenge for any robot dynamics, but actually turned out that for ground vehicle, whatever friction model you can claim that this is more accurate, they are all wrong. There's no exactly correct friction model. So what you are doing is that before you actually train the neural network actually to correctly compensate for whatever changes, you also have a visual foundation model features to actually correctly distinguish between night and daytime, the grass field and rock field. So this is a jet propulsion laboratory Mars yard where actually Curiosity, Perseverance rovers were tested. And you actually see that when you go over different terrain, we can actually, visual foundation model can correctly pick up this distinction. So I just wanted to mention that although it's not really spacecraft, and also a quick extension of that is also you can use a Monte Carlo tree search to kind of see for spacecraft when you have failures in the thrusters, and you might actually don't know whether you have failures in sensors or you have failures in the spacecraft actuators like reaction wheels and a number of different thrusters. So you have a quick estimation method, and this is called the active sensing because you have to fire thrusters to kind of identify which one actually really failed and do a quick tree-based search and estimation. So I don't think that I have a lot of time, but we have a fly project with the Aerospace Corporation. In my opinion, the best organization that's building the best CubeSat is the Aerospace Corporation of the US, but they are, of course, a nonprofit organization. So we are working with them to put the autonomy software in the system. So the first mission is being launched, the Node Light is and then basically what you are doing is that a lot of like a pose estimation and shape estimation and tracking problem for actual object. And we are doing basically ROS-based system, and we have a kind of embedded computer that was kind of radiation hard, and that they can support some real-time training of even some neural network in space. So, and this is our spacecraft simulation lab. Obviously, it has a bunch of this breadboard-based kind of a box that actually has all the sensors. And I can tell you that it has I call that as a Ferrari of a CubeSat. It has even radar, LiDAR, and multiple cameras, including sonar cameras. And this is a spacecraft model where we can generate this, very similar to Spark challenge, where we can actually generate the actual model of the spacecraft. So just the next 2 minutes, I have to end my lecture. So this is like a conventional post-estimation problem. This is very relevant to this community now. We are talking about launching a multiple spacecraft around the certain target. It could be asteroid, interstellar object, or it can be a malfunctioning big satellite. The problem is that if you actually do a multiple spacecraft, and then somehow you have to generate the a shape using multiple features, basically it's not scalable. So that's a big problem. And another thing is that you have multiple graphs, including relative estimation, also communication. So when you talk about this consensus or graph, you have two edges. One is a communication graph and relative kind of vision-based kind of observation. So we can kind of include all of that. The key message here is that, yes, this is a more conventional extended Kalman filter or Kalman information filter-based kind of a consensus. But so it might be optimal, but obviously it's not scalable. So the number of measurements and state, it kind of increasing dramatically. So how can you actually solve that problem? By the way, this is experimental validation of this method. And obviously, although we are doing a lot of segmentation and feature extraction using computer vision, we are more focused on estimation problems. So here we are using the April tax. So some of the work, and we can show that this is pretty good method for a small number of spacecraft, and the actual target doesn't really have many states. But so it's not scalable. So I want to finally close my talk. And so essentially it's a SLAM problem because you have to estimate the shape of your target, not just generating the a few points. So a lot of shadowing problem, orbital dynamics. So that's why we can solve this problem using maybe shooting different side of sensors, and also a lot of different learning-based methods, even taking care of shadowing problem. So I want to kind of shamelessly mention that I have this theoretical paper, Automatica 2018, how to properly do multiple Bayesian, because whether it's a particle filter and Kalman filter, it's actually Bayesian filter approximation, right? So it turned out that the best way of doing this is that you basically do the logarithmic opinion pool instead of all this algebraic linear consensus. So this is called the lean OP. Is a conventional consensus problem where alpha there is basically kind of a game, but instead of doing that, you have to get the geometric mean. Then you can actually turn out the mathematical proof that it's going to minimize the KL divergence between whatever optimized solution and all the individual measurement, which means that you have to propagate the likelihood function, including measurement, to the individual neighbors. And then obviously this is a general for nonlinear dynamics and non-Gaussian models for Bayesian approximation. And then so we can actually derive the Kalman information kind of approximation, which is right here. So we actually applied that to MSAT. So I think this is actually has been proven. I just end my talk. The recent paper in 2023 is that I was big fan of this kind of filtering approach, but recent trend in the SLAM, it's been already maybe 10, 20 years, is actually factor graph. What I mean by that is that obviously, okay, so all these convergence issues might be actually mitigated by actually solving the direct optimization problem using factor graphs, right? So but obviously, original factor graph by this paper, if I have the reference here, I don't. So it was initially derived for like offline kind of a SLAM problem, right? So we basically include a nonlinear dynamics, nonlinear measurement model. The whole idea is that for multi-agent, multi-spacecraft problem, how you actually do this joint kind of a factor and locally coupled kind of factor, kind of incorporate that as a constraint, and then do solve this problem. So basically, we are using this kind of decomposition problem method, very well known, like alternating direction of a method of multipliers. Obviously, this is called ADMM, and then we actually show that we can actually successfully combine the GT-STEM, like a factor graph optimization, with ADMM, and obviously there are details. Furthermore, as I said earlier in the title of the talk, we actually proved the exponential convergence of this method, provided that its original cost function is strongly convex. If it's just convex, which is often the case, you actually have a 1 over k convergence. So really fast, but obviously for benchmark SLAM problem, it showed that it actually works very effectively. And also, as you increase the number of states, it doesn't really scale badly. It's basically stay constant. So I think there is a final method is that obviously the vector graph and DFGO and using ADMM is kind of open method, and then we can actually extend that to the ISTEM, which is kind of incremental version, real-time version, because as your time goes to the left to the right, you can actually modify. You can see the axis here. You can actually apply that, but it's not just straightforward extension of ISAM. So we had to do multiple modifications, both in the FGO vector graph optimization stage, and then how you actually define the augmented vector update. So that's the new TRO paper, transaction stone robotics, and obviously benchmark SLAM problem. It kind of showed that it actually works pretty effectively, and then it's gonna hopefully work for spacecraft. That's what we are working on. So it was pretty fast, and then so hopefully you will see more detail by finding my papers with my students. And so thank you so much for listening to me.
Maybe you have time for one.
I'll stay for any additional questions throughout this workshop. So
Yeah, maybe you can.
yeah, thank you so much.
Thank you.
Okay, so now we'll move on to the spotlight presentations from the presenters. This will be a really quick 4 minutes presentations with 1 minute for transition. If you have any questions, please save it for the interactive poster session that will happen right after. And if you are in the Zoom, I suggest that you reach out to the presenters as well after this session. So without further ado, we'll first start with the first paper, Robust Perspective and Crater for Crater-Based Camera Pose Estimation, presented by Sophia McLeod from University of Adelaide.
Hi, everyone. My name is Sophia. I'm one of TJ's students, and I did the work Robust Perspective and Crater for Crater-Based Pose Estimation. There is this existing pipeline. It's called the Crater-Based Pose Estimation Pipeline, and it's been traditionally used or looking to be used for things like lunar survey missions, for example, where we're trying to estimate the pose of our spacecraft, of our satellite, through taking pictures of the surface of the moon. So the structure of this pipeline is that the orbiter takes an image of the surface of the moon. We use a crater detection algorithm to detect the craters through the image. And then we use a crater matching algorithm to match those craters to known craters in a crater catalog. From these crater matches, then we use a pose estimation method to estimate the camera pose and hence the satellite pose, which can then also be used to estimate what we're observing on the surface and where that's actually located on the surface of the moon. So my area is actually within the pose estimation section of this pipeline. Previous methods tend to only really ever look at the crater detection algorithm and crater matching algorithm, with far less attention on the pose estimation step of this process. And the way that the pose estimation is currently done in these previous methods kind of use loose coupling of position attitude optimization. They don't account for incorrect crater matches, or they use geometrically invalid objective functions for estimation like PNP, with the 2D imaged ellipse center matching to the 3D crater rim center, which is not geometrically aligned. So to address these weaknesses, this particular paper that I worked on produces something called PNC, Perspective and Crater, that estimates all 6 degrees of freedom of the camera pose from crater correspondences. So our method minimizes the reprojection error of craters represented in a geometrically meaningful format, which is a conic or an ellipse, and uses M estimators to also account for crater matches. In addition to that, we've also produced a new data set called Crescent. It consists of images from 4 different lunar regions on the moon's surface of the highest resolution DEM that we have of the moon's surface. So it's about 5,000 plus synthetic images generated of the moon at an orbiter altitude of about 100 kilometers off the surface of the moon, which is kind of the expected conditions of a surveillance mission. And the images were taken at increasing angles off nadir, so from 0 to 60 degrees in increments of 10 degrees, which is also quite unique for this kind of data set, as these data sets tend to only look at nadir facing. The results and conclusions from this, we've compared against existing methods and then compared against different objective function metrics that we used in the PNC approach. And we can see that our proposed PNC algorithm invoking the EP, which is ellipse parameter distance, error function achieved the most accurate results and also significantly outperformed existing pose estimation methods for crater-based pose estimation, highlighting the necessity of having a really good pose estimation algorithm implemented in these previous works as well. And we also learned a little bit more about the situation setup and what situations are really good for estimating pose accurately. For example, images taken at 20 degrees off nadir tend to produce the most accurate position estimates. That's all from me. Thank you.
Right. Next is exploring AI-based satellite pose estimation from novel synthetic dataset to in-depth performance evaluation, presented by Fabienne Gaillet from IRT Saint-Exupéry.
I think I didn't share my slides.
Yep, it's there.
Okay. So good morning. My name is Fabien Gallet, and I'm representing the IRT Saint-Exupéry, the French Research Institute, and Thales AI4Space as the main contributor of the project. I'd like to introduce you to a new synthetic dataset called Raptor, containing space rendezvous scenes and proposition of performance metrics for the design and testing of pose estimation solutions. The dataset has been released, and everyone can get it freely by following the provided link. The work is related to pose estimation for space rendezvous where the target spacecraft model is known. It doesn't focuses on the estimator itself, but with the point of view of a system integrator on how to provide, on one side, high quality data, and on the other side, how to assess performance of the solution. The dataset provides some exclusive features. For instance, a physically based rendering engine is coupled with high fidelity sensor model, providing radiometrically accurate synthetic camera outputs. And in addition, camera outputs are joined with masks, distance maps, and normal maps, helping to create multitask solutions. Another specificity of the dataset is the extended distribution of relative poses. For instance, the distance is drawn from 20 to 100 meters, and there is an effort to uniformize the client spacecraft position inside the image frame. The main dataset of 100,000 images contains typical situations with nominal parameters, and a complementary test split of 20,000 images has been added with augmented scatterings, allowing to test solution with degraded images acquisitions. For instance, with bad exposure, blur level, high blur level, noise level, and worn material optical properties. On the other side, the metrics tries to answer two main questions. First, how to characterize performances with respect to the distance, and how to define and discriminate outliers. For the first question, the performance law is approximated using 90% quantile versus distance, and the outliers are directly estimated in the 6 dimensions of the pose estimation using Mahalanobis distance. Outliers are also defined outside the Mahalanobis theoretical 99% quantile. So we happily shared this dataset, hoping it will help to facilitate the development of further spacecraft road estimation solution. And thank you for your attention, and I will be pleased to answer your questions at the poster session.
Next, we have optimized Martian dust displacement detection using explainable machine learning by Anna from DL.
Hello. So my name is Anna. I'm a PhD student at German Aerospace Center, and I'm also in the team of Mars Science Lab, meaning that we work on the Martian in situ data acquired by Curiosity rover. Now, more about the data sets that we work on. So this is a Curiosity rover, and this has been on Mars since 2012, and it has multiple scientific measurements attached to it to look for the signs of past habitability of the Mars. The instrument that I'm working on is mounted in the head, and it's called CAM-CAM. CAM-CAM translates into chemistry and camera, and it consists of two parts. The first part is a LIB, so laser-induced breakdown spectrometer, and it's responsible for retrieving elemental composition of the target. And the second instrument is RMI, remote microimagers, that takes context images before and after LIBS measurements are done. Now, from this small figure here, we have how LIBS works. So it shoots a laser, powerful laser, and it creates a light-emitting plasma. And then a spectrometer collects this light-emitting plasma, and we can retrieve elemental composition of the target. But when the laser is shot, because it's powerful, it also produces a shock wave, and shock wave sometimes displaces dust from the target. Now, the dust displacement is a good thing because if the target is dusty and the shock wave removes the dust from the target, we have a better target laser coupling. So we can retrieve the elemental composition of the target and not from the dust. And my task was to detect whether this dust displacement occurred during LIBS measurements, according from the images taken before and after LIBS measurements. So here we have in figure 3 before and after is also, we see that there are 5 shots of LIBS, and around it there is a circle just to point to the dust displacement. So we tried different models, and the problem also was a limited data set. So in total, CAM-CAM acquired 4,000 images, and there are no labels whatsoever. So we had to label some of them, and we labeled 200 images per class and created a binary classifier that was a 2-stage model. And we inputted both before and after LIBS images. We did some pre-processing, so we found the difference image just to emphasize the difference between the images, and then we extracted feature maps from the VGG16. We flattened those feature maps and fed to the random forest and created a binary classifier that achieved 92% accuracy. We also explored explainable AI. We wanted to check if all the feature maps are important, and we checked the feature importance and checked the dependence of the model accuracy to the number of features, and we also checked the Shapley values to prove the point. We also explored the guided propagation just to visualize what was learned from the optimized network, and these are the patterns. So the dust displacement was learned from the model, and more about the application and more details about this work you can find in poster 82. Thank you.
Next is mitigating challenges of the space environment for onboard artificial intelligence, design overview for a recently launched payload by Jonathan Morgan.
Hello, my name is Jonathan Morgan. I'm an engineer at the Melbourne Space Lab. Okay, what have I done? I'd like to acknowledge that I live and work on unceded lands of the Wurundjeri Woiwurrung people, and I pay my respects to their elders past and present. MSL is a lab at Melbourne University. We focus on instrumentation for nanosatellites, including edge computing and AI. Spirit is our second project to reach space. It launched into sun-synchronous orbit December last year. And Loris is the imaging payload on board Spirit. It includes a low-power GPU, the NVIDIA Jetson Nano. And the main goals are images for outreach and spacecraft monitoring, including evaluating the performance of the radiators using thermal infrared, and as an edge AI testbed in collaboration with the computer science group at Melbourne Uni. So we currently host a very simple cloud detection model with planned experiments on on-orbit fine-tuning. The motivation for this work is to focus on highlighting the unique challenges of actually deploying edge computing in space, particularly for small-scale nanosatellites. So the main challenges we focused on were the radiation, thermal management, and the very limited transmission bandwidth. So the key theme is the importance of modeling this environment to accurately understand the challenge and then inform the mitigation steps, both in the design stage and in operations planning. So in radiation, we modeled the environment for single event upsets, as well as for the total ionizing dose over the mission, and then chose the amount of shielding that would bring the TID below what previous work found was survivable. We also have software monitoring routines to check if memory is being corrupted. And then operationally, we avoid the high radiation zones, including the poles and the SAA, the South Atlantic anomaly. Thermal management is very important for electronics in orbit. The platform design needs to make sure the electronics do not go below survival temperatures when the spacecraft is inactive and in eclipse. And the lack of convection in space means that the electronics have a harder time rejecting heat. So if you ever see a spacecraft with finned heat sinks, then you know they haven't got a thermal engineer on board. So we used the aluminium frame that was the radiation shielding to be a heat sink to increase the thermal inertia of the spacecraft electronics and then also conduct the heat away. Key point is that we had to thermally sink more components than what is standard in atmosphere. So for example, the power management IC on board the Jetson Nano is not heat sunk normally, but in vacuum it needs to be. Currently, Spirit is still operating on its purely primary UHF comms, which gives us about 80 kilobytes per day in total on average today. We've got 9 cameras on board, so obviously we can generate significantly more data than that. The primary way we're using image compression to enable us to get more images and more useful images down is using JPEG XL, which is a next generation image codec, including with progressive coding. So that means that we can get a 1% image preview with the very first, say, 2 kilobytes of the image, and then progressively download more and more to improve the quality of the image up to the point that we need. And then we're also working towards using on-orbit fine-tuning of our very simple cloud detection model as a proof of concept where we don't download the images, but we use the metadata of the time and pose of the satellite to generate a ground truth label that we can then upload to facilitate fine-tuning with more data than we could download and label ourselves. Come and chat more. If you'd like to run something on the Jetson Nano that's in space right now, come and talk to me. If it's very small and we can upload it, that would be a fun thing to do.
Next paper is a dual mode approach for lunar-based navigation in a lunar landing scenario presented by Roberto Del Puente.
Thanks so much for the introduction. I'm Roberto Del Prete from the University of Napoli Federico II, and this work has been conducted in collaboration with Telespazio, an Italian company, and it is with vision-based navigation for lunar landing scenario. So we already know the problem of terrain in relative navigation exploiting surface observables, and so far this has been approached with many sensors, including LiDAR, monocular cameras, and altimeters. When we deal with monocular cameras, this problem is also called vision-based navigation, and this is the kind of stream that we get when a camera is mounted on board the spacecraft. But we need efficient methods and tools to process this stream of data. And Johnson is his revisions of in 2008, he groups these methods in correlation-based and pattern matching-based. Each one of them with its pros and cons. For instance, the correlation-based are easy to implement on FPGAs, and they are computationally effective, but they require to have landmarks close to the landing site, and are highly sensitive to the surface reflectances changes. Plus, they require a map on board the satellite. Pattern matching based, on contrary, they are not very sensitive to the changes in lightning, but are more challenging to deploy on FPGA and are computationally more expensive, and require to have landmarks on the landing site. For both methodologies, they do not account surface changing during the orbit motion, because lighting conditions can be varying, and because we can have areas with few or no landmark features. So that's why we propose a dual mode vision-based navigation approach, in which we have an absolute mode, which is the one that we've seen before with clutter detection, matching, and post-estimation solving, and a relative mode, which is a bit different. So for the absolute mode, we use a standard object detection technique, and we use the clutter matching approach as detailed in the projective invariance paper of Christian et al. And finally, we use efficient perspective endpoint solver to have our pose. For the relative, we used a combination of convolutional neural network for key point extraction and description, and graph neural network for the matching assignments. We finally computed the essential metrics, and by using the measurements from an altimeter, we solved the scale ambiguity problems, and we output a relative pose estimation. To test our system, we develop a testing scenario targeting an orbit during the descending phase towards the Shackleton rim. For the absolute phase, we used a circular orbit at 15 kilometers of altitude, while for the relative phase, we start at 10 kilometers and we're going down to the main braking phase to the 2 kilometers. So we used our in-house simulator using Unreal Engine to use ray tracing techniques and having highly realistic lighting conditions. And our preliminary results show that we have an overall descending trend with lowering the altitude, and we achieve a mean positional accuracy of 270 meters for the absolute mode, and 27 meters and 1 meter for the mean horizontal displacement and vertical displacement error for the relative mode. We finally estimated the errors on the altitude, simulating a 30-degree yaw-slew maneuver along the trajectory. And our results show an average error of 0.027 degree with a maximum deviation below 1 degree. We finally test promising results for deploying these modules on space-graded hardware. Indeed, we deployed the clutter detection module on Neural Compute 6U and the Cognizant XU1, and we demonstrate inference time below 1 second. The main takeaway is that the NCS2 is 3 times faster of the XU1 with an average precision of 0.67. To download the data, I invite you to scan the QR code, and for other question and discussion, I invite you to join me at the poster session. Thanks.
Okay, next is tackling the satellite downlink bottleneck with federated onboard learning of image compression by Gabriele Milli.
Okay, technical problems as usual, but my computer is not sharing. Let's start now. Okay, sorry for the inconvenience. And my name is Gabriele Meoni, and I am presenting this work that I've done in collaboration with my colleague Pablo Gomez. So, well, we start with the idea that downlink is becoming an issue depending on the mission. So, well, if you consider the only Copernicus data, the Copernicus mission satellites are downloading nowadays around 20 terabytes of data. But of course, if you consider the Copernicus missions, they don't have downlink problems most of the time. They are quite, let's say, downlink requirements are well covered, but that might be not the case for commercial missions, especially if they have a small sats, they have a limited access to the ground segment. Okay, nowadays AI has been used a lot to try to, let's say, diminish the amount of data that you want to send on the ground. Well, this approach is very interesting, of course, and it's very suitable for early alert missions where you want to send data quickly and all the actionable information, but it might be not the best approach when you actually want to send a lot of data. For instance, when you have commercial or scientific missions where the data is basically what you want. So we basically try now that approach that we call LICOS. LICOS is the algorithm for learning image compression on board satellite constellations. So what's the idea? We have a constellation of satellites, and we train by using federated learning and a deep compression model. So the model is basically distributed on board the satellites. They don't share the data, they just share the models. And when they pass over the ground segment, they share the weights. So during the time, basically the model improves. And in the end, you have a model that works on board. So what's the idea? The idea is that you can tune basically the goodness of the quality of the image versus compression rate, but at the same, but you can also do something different. You can also send very compressed image to the ground that are your basically previews, and then on the ground you select the image of interest and you ask for the raw data for the ones for which you need zero, for instance, loss of information. So to simulate these scenarios, we use we consider a constellation having 3 satellites in Sentinel-2-like orbits. And in particular, we train on Sentinel-2 raw data, and the data that we produce is called TROS. And we use by using a true approach. First of all, the model that we are training is an autoencoder provided by Compress AI framework. And being an autoencoder, you don't need labels. That's why it's also very easy to train on board. And in particular, we use 2 settings. One is called split, where all the Sentinel-2 bands are basically compressed separately. The other one is called merge, where the bands are compressed all together. But since the bands have a different spatial resolution, we have to, for example, all of them to like an intermediate resolution that's 20 meters and then compress all together. The satellite that we use basically have the setup that you can see in the image. So there are CubeSat 6U CubeSat, and they have 3 ground stations that are the one used in the Sentinel-2 basically missions. But of course, when you train on board, and we saw in a presentation, or when you perform onboard processing, you always have problems of power, limited line of sight, and also temperature. And to model that, we use our software that we developed in a previous study. It's called PASSELS. So as you can see, you have a simulation of PASSELS for the Sentinel-2 missions, where you can see the satellites when the software knows when the satellites are in line of sight with the ground stations. So if you want to try it, you can actually try it and download it for free. So here are some results. So we compare our models to JPEG, that we are well aware that is not the standard for compression on board, but it's a starting point to compare with. And in particular, we compare in terms of PSNR, SSIN, and also compression ratio. So basically the file of the size after compression divided by the size before compression. So as you can see in the image, if you take a look at the first 2 images, basically on the first 2 rows, well, you will see that our model outperformed JPEG, but not that much. But when you compare to the last images, where actually so there's much less information, our model works quite well. And in particular, the compression ratio is much higher for better metrics. We have also simulation of the impact of the other parameters that I don't have time to discuss now, but I will be more than happy to discuss over the poster session. If you want to try our software, please. Thank you very much.
Okay, next is Transformers for Orbit Determination, Anomaly Detection, and Classification by Matthew Popple. Oops, sorry about that.
All right, cool. Thanks for the introduction. Like I said, my name is Matt Popwell. I'm presenting, the primary author is actually Dr. Nathan Parrish-Ray. I'm presenting on his behalf. And this is Transformers for Orbit Determination, Anomaly Detection, and Classification. So for some context on the problem, traditional spacecraft navigation combines astrometric measurements and a Kalman filter to estimate a spacecraft's position and velocity. Like Dr. Chung said this morning, those Kalman filters aren't bulletproof. So much of the success of traditional navigation comes down to operator experience guiding these filters towards a good solution. So when issues pop up, identifying and correcting them is a very time-consuming process. So this problem offers a natural opportunity to use supervised learning to identify what's going on, what's going wrong in these filters. So some more context on the problem. Nominal filter performance will produce residuals that are normally distributed and centered at zero. So kind of that first plot at the top, the blue dots there. And then if something's going wrong, we'll actually see a trend in those residuals. So that's the bottom plot. So the question is, can we train an ML model to ingest this data and identify what mismodels may be occurring? So I'll kind of skip through these next slides quickly, but for the training data, we identified 5 anomaly classes that we normally see in spacecraft operations. And for each anomaly class, we generated 20,000 trajectories and measurement simulations. And then the model ingests things like the epoch, the observing station state, and those residuals. We looked at 3 model architectures. All are based on the transformer model introduced by Google. All use a class token, and all of them use the time to Beck algorithm to replace the traditional positional encoding with a time encoding. So the first is a measurement transformer, which is just an encoder only. It takes all the navigation data we have, concatenates it together, and passes it through. Then we have a tracking path transformer, which is 2 nested encoders. And this lets us pull out unique information from each tracking path. So we'll, and jump back a bit. We normally see these big, well, we jump back on my end. It looks like it froze. There's a delay. Yep. All right. I'll just skip ahead. We normally see it's pretty sparse and we get these big gaps between tracking passes. Spacecraft comes in view, comes out of view. So this lets us pull out information from each pass. And then the last was the vision transformer. This is just the straight out of Google Vit. And what we do is each feature we represent as a channel in what we call a hyper image. So the results, we found that each model achieves at least an 80% validation accuracy. That tracking path transformer with the 2 encoders achieves a 93% validation accuracy. The biggest confusion is between the drag, gravity, and nominal mismodel classes, and we can readily explain that with physics and operator intuition. And we did some hyperparameter tuning, and that allowed us to reduce the model sizes down to single-digit megabytes for deployment on hardware. And so the last thing we're super excited to talk about, so Advanced Space, just for reference, owns and operates Capstone, which is a CubeSat flying at in an NRHO at the moon. In February and March of this year, we deployed the measurement transformer on Capstone. We uplinked it and tested it successfully. To the best of our knowledge, this is the first time a transformer model has flown in space and the first time ML has flown beyond Earth's orbit. So if you have any questions about any of that sort of stuff, or you want to fly your own ML model on Capstone, come talk to me or shoot us an email. Thanks.
Okay, next we have Deploying Machine Learning Anomaly Detection Models to Flight-Ready AI Boards by James Burke.
Are you silent Zoom? We can share it there.
Yeah.
Oh, I didn't join. Sorry.
You joined. Right.
Okay, so I'm James Murphy. I'm here from Rail to Space Systems Engineering based in Dublin, Ireland, and my project is working on deploying multiple different types of machine learning models to flight-ready boards, boards that have flown or boards that are on the development process to be flown. To do this project, I worked heavily with Ubotica, which I've seen a few people before me have already worked with, and as well at Aviva based in the UK. It's also in conjunction with University College Dublin, who's just recently flown their first CubeSat. So what's the problem here? We've got onboard telemetry. We can't access a lot of it. And for a lot of space missions, we have very low power budgets and SWAT constraints. If you're going to deploy an anomaly detection model on a small sat, you're also not going to be a payload. So you're even more restricted when it comes to power. An example here is AirSat-1 under construction. You can see how small a 2U CubeSat actually is if you haven't seen them before. Other issues come trying to deploy your models on specified hardware. I encountered a lot of problems trying to deploy certain architectures on certain boards through this work. So it's something worth bearing in mind throughout the process. So what's the goal here? Well, we want to determine what the optimal model is for detecting anomalies in satellite telemetry, and we want to determine what board we will fly it on. So there could be a trade-off here at the end. So what did I do in this work? I deployed multiple deep learning models and multiple classical learning models to compare and contrast the effect that the different model architectures have on the different hardware. So to do this, we also used the data set supplied by JPL from 2018, containing SMAP telemetry and MSL telemetry. All in all, there were 76 channels of data with labeled anomalies that we could train our models either supervised, semi-supervised, or completely unsupervised, depending on the model architecture. We also deployed it on a multitude of boards. So we deployed it on Ubotica's XE1 and XE2, which have the Myriad 2 and Myriad X architectures. We deployed it on an NVIDIA Jetson Nano, Google Coral, and just for fun, a Raspberry Pi. All boards, though, have either flown, have plans to fly, or are in the process of being qualified for flight. So I had to cut this table in half because of the shape of the slides, but if you want to see the full one, please come and talk to me at the poster. We did find some interesting results here where we weren't really looking for the best model performance here. We were seeing how it gets affected based on which board it goes to. So these are pretty basic models. But generally across the board, we found some of the best models were transformers or LSTM autoencoders, but then they also were the hardest to deploy on some of the boards. Some boards wouldn't take the architecture at all. So if you want to talk to me more about this, come find me at poster number 87. Thank you.
Okay, next is cross-temporal spectrogram autoencoder, unsupervised dimensionality reduction for clustering gravitational wave glitches by Ely.
So hello, I'm Yili from Northwestern University. Now let me introduce our cross-temporal spectrogram autoencoder, an unsupervised dimensionality reduction for clustering the gravitational wave glitches. As the advance of the LIGO, the gravitational wave has been successfully detected and confirmed. However, the gravitational wave signals are usually weak. That's the reason why the LIGO is highly sensitive. That means when capturing the correct gravitational wave, it can also capture some non-Gaussian blurs, which we call the glitches. In the right figure is an example of the glitch. This presents significant challenges to the clarity and reliability of the gravitational wave detections. That's the reason why we need the Gravity Spy project, that is, to classify the glitches by volunteers' effort. However, there are two main problems of this project. One problem is that it's not scalable. The volunteers cannot just label all of the data. Besides, a more severe problem is that the pattern of the glitch can change over time. Even though we train a classifier based on the data labeled by the volunteers, in the future, as the glitch change, the classifier can still fail. Therefore, we need an unsupervised method, our cross-temporal spectrogram autoencoder. Since the input are 4 spectrograms in different time duration, we develop a 4-branch autoencoder, as is shown in the top left figure. The 4 spectrograms are first fed to 4 encoders to extract the 4 low-dimensional latent codes. These 4 low-dimensional latent codes are fused by several NLP layers into a single latent code. This latent code is then shared by the 4 different decoders to reconstruct the spectrograms. The reconstructed result, as well as the input, are used to calculate the MSE loss. So, as you can see, the whole procedure in the training is unsupervised. Only standard autoencoder loss is used, and no class label is supplied. After training, the single latent code is used to cluster different glitches. To build each branch, we integrate a convolution neural network and a vision transformer, as is shown in the bottom right figure. Following the conformer, the CNN part and the VIT part is bridged by the upsampling and downsampling blocks. For multi-branches, we communicate these branches by our novel CLS fusion module. We propose this CLS fusion module using a shared CLS token to first query all patch tokens to gather global information from all 4 branches. The detail can be shown in the following equation and in the right figure. Then this CLS token is concatenated back to each branch to provide the abstract and global information. Within each branch, a standard self-attention is used. And so here is some result we test on the GravitiSpy O3 datasets. Since we are the first to propose an unsupervised method, we compare the state of our semi-supervised method. So, which includes the direct and VAT. So as you can see in this table, our model outperforms direct by a large margin. And for the VAT, although our methods is not as good as a VAT with 5% of label data, when the label data is only 1%, our models can still achieve the best performance, which means that when the label data is insufficient, which is exactly the case in the future where glitches change, our model can get the best performance. And we conduct some ablation study to verify the integration of CNN and VAT and our CLS fusion module due to the limit of time. So maybe for more detail, please feel free to come to my poster. And here is some qualitative results. And here's the reference. Thank you for listening.
Okay, next is monocular 6 degrees of freedom post-estimation of spacecrafts utilizing self-iterative optimization and motion consistency by Yunfeng Zhang. I'm assuming he's joined from the, yeah.
Hello everyone, my name is Yunfeng Zhang from the Academy of Mathematics and System Science, Chinese Academy of Science. I will introduce my work, monocular 6-dwarf pose estimation of spacecraft utilizing self-interleaved optimization and motion consistency. We focus on the problem in Spark 2024 challenges, spacecraft trajectory estimation. There are 2 main challenges. How to overcome the problem of the different distribution between the training and the testing data, and how to leverage temporary information to estimate the pose. Our work has 3 main contributions and process. Let me introduce them one by one. In the initialized phase, we use a small number of the modularly marked 2D key points to initial the 3D model. We then generate multi-text labels based on the training theta set pose labels. Due to the errors in the initial 3D models, we treat the 3D model as optimization variables. We then optimize the 3D model based on the error between the predict pose and the true pose, and then use the optimized 3D models to further refine the network. Due to the difference in the data distribution, we utilize the motion consistency to smoothing and correlate pseudo labels, enhancing the model's self-training on the test site. Finally, let's introduce our experiment. Our method achieves the competition results compared to other methods. Here are the results of the multi-step iterations of the multi-text labels and the pose estimation before and after smoothing. Thank you for listening.
Okay, next is the paper titled Cross-Space 6D, Leveraging Geometric and Motion Cues for High-Precision Cross-Domain 6 Degrees of Freedom Pose Estimation for Non-Corporate Spacecraft by Jianhong Zuo.
Hello everyone, my name is Jianhong Zuo, and I will now present our paper Cross-Space 6D Leveraging Geometric and Motion Cues for High-Precision Cross-Domain 6D Pose Estimation for Non-Cooperative Spacecrafts. To begin with, the application of molecule vision in estimation the pose of non-corporate spacecraft has garnered significant attention. However, there are numerous challenges in real-world applications, including cross-domain variation in shape, texture, lighting, and motion pattern between simulated and real capture images. To address these challenges, we propose a novel domain adaptation 6D pose estimation algorithm named Cross-Space 6D, which consists of three main components: segmentation and tracking, pose estimation while template matching, graph-based global localization. First, to mitigate the impact of background interference, we're using mask-to-formal thematic segmentation algorithm and tracking anything in this work designed to achieve high-performance segmentation and produce a bounding box in image sequence. The second is pose estimation by template matching, despite the variability observed in 2D image. The underlying 3D shape remains invariant across both visual and real-world scenarios. News infers the model with the textual information, reconstructs the 3D mesh from simulated images. We utilize the megapose algorithm for template matching, estimates the target pose through 3D reconstruction results. To enhance the accuracy of pose estimation, we introduce a graph-based global localization method that fuse the absolute pose and relative pose. By integrate segmentation and tracking into our BSLAM3 to generate smooth and precise relative pose. However, relative pose has scalar discrepancies and lacking the transformation with the target coordinate system. To address this issue, we employed the graph optimization algorithm to fuse relative pose and with absolute pose. In challenges results section, we use the Spark 2024 dataset to conduct the completed analysis. The proposed pose fusion algorithm transforms the relative pose to the same coordinate system as the absolute pose, can reduce the error of absolute pose compared with to the absolute pose. Fusion pose are smooth and continuity. Compared to the absolute pose with filter, the proposed method reduces orientation error by 68%. In summary, our method addresses the challenge presented by complete sense across different domains in both simulated and real captured images. Cross-Space 60 achieve high precision and demonstrate outstanding performance on the Spark 2024 dataset. Thank you for your listening.
Okay, last but not least, we have Revisiting the Domain Gap Issue in Non-Cooperative Spacecraft Post-Tracking, presented by Kun Liu.
Hello everyone, my name is Liu Kun, and I'm from Nanjing University of Science and Technology. I'm honored to present at the AI4Space. The title of my presentation is Revisiting the Domain Gap Issue in Non-Cooperative Spacecraft Post-Tracking. When applying deep learning to space, the biggest challenge is data quantitation. During ground development, in-orbit images are inaccessible, and in orbit, it's tough to retrieve large volumes of synthetic image due to storage and uplink constraints. Therefore, to close the domain gap, we focused on domain generalization on the ground and source-free domain adaptation in orbit. In this work, we divide the spacecraft pose estimation into 3 phases. These phases correspond to ground development, in-orbit training, and mission exclusion. During offline training, we use data augmentations to improve robustness to illumination and use style augmentation to compensate the lack of textures in synthetic images. In online training, we design a domain adaptation method based on ReSec EPNP. During flight, we use an unscented Kalman filter to estimate the target bounding box. It avoids the impact of domain gap on the target detection network and helps us achieve more accurate pose estimation. Object detection network is used minimally in the entire process. Hence, closing the domain gap focuses on the landmark regression network. We address this by using ReSec EPNP to select inliers and compute pseudo labels and then calculate the loss, specifically the error of outliers. In our work, high precision outputs are used to supervise the low precision outputs. We only update the parameters of the normalization layer in the encoding part. In addition, the bounding boxes should be randomized in this phase. We randomize the vertices of the bounding boxes by 10% of their width and height. In flight phase, UKF is only used to get bounding boxes. Compared with fast RCN, UKF provides more robust bounding boxes, enhancing the stability and the accuracy of pose estimation. As shown in the right video, without bounding box randomization in online training, the landmark regression network becomes extremely sensitive to tiny changes of the bounding box, resulting in tracking failure. Our method is tested on Spark 2024 and Speed Plus datasets. Online training reduces pose error to 1/3 of that in offline training, and accurate target bounding boxes improve the precision of pose estimation shown in flight. However, there are still 2 issues remaining before we can proceed with the in-orbit application. The proposed online training takes long duration to be stable, and the online training is not elevated on additional test set. Thanks for your attention.
Thank you to all Spotlight presenters. We are right back on time. Thanks for that. Thanks for Jeff for his excellent managing of the session. So let's all head to the poster session now. Again, it's level 4, so go up the escalators, look for the Sky Bridge, and then look for exhibit hall 4E and 4F. Hopefully Ethan has retrieved all your posters. You might still have to stick it on the board, but hopefully the posters are there ready for us. If not, go to the poster distribution center. There's also coffee, I think, in the exhibit hall. All right, see you all there.
From University of Rome, and since 2003 is working at the European Space Agency. He is an expert on onboard data handling and is conducting a lot of research and development activities on onboard data handling problems, including artificial intelligence on board satellite, of which he will speak diffusely today, basically. And he co-authored more than 100 publications, and I will not waste more time, and I will leave the floor to Gianluca. Please, Gianluca, the floor is yours.
First, a check. Can you hear me?
Yes.
Can you see the right screen?
Is that the right screen?
Yes.
I think that's the right screen, yeah.
Yes.
Okay. Fantastic. That's it's already a very good start. I'm very sorry not to be there. I heard from Gabriele you're having lots of fun, and I could see a lot of extremely interesting presentations. So I won't delve into the very technical domain phrase, more a discussion on is it really a good idea to put AI in space? Of course, the answer is yes, so I don't think this is a big spoiler for you. The problem is that while everybody agrees this is a good idea, we have been seeing very little happening, at least in the past 3-4 years. I'm very happy that Gabriele is there. Gabriele spearheaded the first ideas that we had these some years ago. So he knows how difficult is this chasm from ideas to reality. The idea behind the AI space, for those old enough like me to remember Stanley Kubrick's movies, it's already there since quite a while. The reality in terms of what we call nowadays AI, that's mostly machine learning, it's a fact, the fact that this can be used in really a lot of spacefaring domain, and a lot of different AIs are at stake. Being a conference of image processing, let's focus a bit more on what image processing may mean in space domain. There are applications like debris removal, in-orbit surfacing that are very specific in image processing for, we call it navigation or pose estimation. For robotic, clearly, online camera processing in flight is extremely useful. Or simply for scientific mission like identification of craters, boulders. We have seen, I've seen something shown today. In general, all the domain of payload processing, especially on the edge, revolves towards something that needs to be done in short term to achieve some information that either be used on board or very quickly by some users. This is extremely interesting, and what is interesting because it it allows to see the difference between general application of image processing techniques. I'm taking here a very simple example, super resolution. At the beginning, it looked a very good idea. We did a lot of experiment with super resolution on ESA satellites. Then at the end, it's more or less what for. Super resolution, compression, a lot of simple techniques just change the quality of an image, but still foresee to have a human looking at the higher resolution, lower resolution image. So doesn't change that much the process of what we are doing. And those techniques are more mature for ground data processing. So I'm not saying that's useless, but you do it on your ground data where you have all your data series that helps the learning of super resolution techniques. The real challenge is to bring those techniques on board of satellites. One example is if you want to do a recognition of objects, especially in the deep sea. Deep sea is important because normally we don't image deep sea because of bottlenecks in data transfer with all our Earth observation satellites. But there's a lot of interesting things happening in deep sea, and direct ship recognition is one. This is a relatively simple problem if you apply it to optical, a bit more complex if you apply it to SAR, even more complex if you want to do tip and cue between optical and SAR, but it enables a new set of services to directly to the user. Very hot from the press. I literally added this slide 1 hour ago, and this is a mission that we have launched together with Open Cosmos Robotica 2 months ago, and it has been proven not only the AI ship detection, but the transmission of the ship positions directly to a smartphone, as a matter of fact, in the space of minutes. This is the type of application we want to enable with AI on board. And why AI? We know that we understood that onboard data processing has significant potential, enables this low latency service. But the first problem, I put it as third, that those increased data processing capabilities are necessary. AI helps us in putting extremely complex algorithm with the limited onboard processing capability we generally have on satellites. There are some showstoppers. First is data standardization. Every space sensor has its own format. I cannot reuse a lot of the algorithm. This is a useless hurdle nowadays. It needs to be tackled. Another problem is if you implement AI processing on ground and it doesn't work, you can always update. Updating it in space is much more complex. On top of that, if you want to save multiple algorithms, if you want to save data series, you want to save history, you need to expand a lot your onboard memories. These are the biggest challenge around. There are much more, like the fact that you are in space, there are radiation, there are limits in the power you can use, the limit in size of the equipment, temperature streams, but these are in the fact that we have already hit the limit in terms of performance in space that we are seeing more or less on ground application as well.
Gianluca, we lost you for 3 minutes or even more when you were speaking about ship detection. So maybe you can restart.
I'll go back then. Sorry for that.
No, it's our fault. Our Wi-Fi dropped, basically.
This ship detection?
Yes, please.
Okay, I'll restart from here. So I just said that super resolution is maybe not the good example of how we see AI in space, mostly because it already hits something we're already doing. It's just a more powerful tool to provide to human users a better image to look at. What we want to do is to do something directly on board that provides low latency services to the potential user. One example that is relevant is direct ship negotiation. While it's very relevant, because normally we don't image the open seas because of data throughput bottlenecks. 2/3 of the Earth are covered by sea. We save in this way 2/3 of data. But a lot of interesting things are happening on the sea, and ship recognition has a huge value to tackle illegal fishing, to tackle pollution, to tackle marine traffic. There are challenges, but in terms of image recognition, the challenges are relatively easy to solve. I wanted to show you, this is the second time I do it, but it is worth something that's really fresh from the press. I added this slide slightly more than 1 hour ago. We received those data Friday last week from a common mission we are doing with the Open Cosmos and Robotica, launched 2 months ago. These are the first data. As you see, it's a fairly low resolution image of the port of Jeddah in Saudi Arabia, where the onboard AI ship detection can recognize can count and give the position of the ships and transmit it to ground. To ground, I mean directly to the 4G, the 5G network in a couple of minutes. This, of course, enables a lot of applications. We are aware of the challenges, and there are some challenges. These are what I'm talking about. So the potential is clear. When you have low latency services, you have immediately a global market if you are in space. The problem we have that every time we fly a sensor, being this optical, being this radar, we have different performance, data formats, communication means. This is a bottleneck for onboard processing with unique algorithms. We need more onboard processing. We still rely on old 2 or 3 generation old processors in space. The situation is improving, but in the case we have the radiation and power bottleneck. When one of your algorithm doesn't work on your computer, in 20 seconds you can update it. If you have to do it on a spacecraft, it's complex. So you probably have to design your network more in a way that it's agile for update than in terms of performance. On top of that, you have to add a trustworthiness layer to be sure that you don't lose data, you don't have false positives, false negatives, or at least you reduce that. This relies also on having much larger onboard memories for data storage, for calculating differences, for automated target recognition. The fact that we need more processing power is something that we know since a while. We are seeing this picture is very famous, but it's a trend of what you're seeing on ground. The same trend with much less points can be seen in space. We have a huge limit in terms of, especially in terms of power that can be dissipated on a single chip that gives us a limit on the maximum frequency we can have on a single device. And that's where AI generated application help. And to give you an idea of the potential economic value that you get when you are able to put AI in the whole end-to-end business of space, I took this data from a study done for the World Economic Forum by Deloitte. They estimate that the full chain of economy linked to the Earth observation data acquisition, we're talking Earth observation only here, is applicable to a lot of domains, but Earth observation is the most striking one, increases the value of those data 150 times. That means in 2030 an impact on the order of $750 billion, mostly, if you take only the light blue thing, in agriculture, due to climate change, due to reduction in population in developed countries, and due to the increase of population in the world, agriculture needs to be more and more automated and needs more and more insight and data. This insight can come only from space in global scale. So the message, the first big message here is that space is moving from delivering pixels, so images, very nice images to the user, to solution. And the solutions means the insights needs to be extracted from pixels from artificial intelligence algorithm. So the point of this intermediation, that's a very difficult word that we use, is the idea of moving completely the future Earth observation from simply taking an image to the combination of artificial intelligence, cloud computer, data fusion. So you can have, there is more information in the fusion of two sensors than on the two sensors separate. And also autonomous tasking, the satellites that are able alone to understand if a target is worth imaging. This idea of acting automatically upon information is extremely complex. And this is the center of what I want to discuss here. What we are doing now. So when a satellite passes over a certain area of the world, if there is something interesting, whatever, it takes minutes, if hours after, the satellite transmits the data to ground. When the data is transmitted to ground, normally our ground stations are polar because our Earth observation satellites are polar. So it takes some time for the ground station to transmit the data to our data centers that are located normally in mainland Europe. This is the case of ESA. In the data center, there are automated algorithms and people transforming this data into something usable. This something usable is then collected by other people to extract insights from the data. Oh, there's a fire. This is a very real image of fires in California 2 years ago. So when this information is validated, this information is transmitted to the authorities that generate an alarm for first responders, civil security service, and so forth. As you see, this is not only long, but it requires a lot of human intervention. What we imagine in the future is that the satellite is capable, and there are two arrows here, is capable to trigger when it sees something anomalous in its sight, and then on board, it has enough intelligence to extract the actionable information. It's not about the pixel. It's not about the image. The image can be even discarded later. But you want to extract the fact that there is a fire. This can be directly sent as an alarm to the first responder, to the is actionable data to the user, and also follow the normal path towards the Earth data center, or also to other satellites that can be rescoped to imagine and this new scenario. But also, and this is the cognitive part of it, it can change the targeting of the same satellite, changing priority to its next path. So, key takeaways from this, because I don't want to take too much of my time. The purpose of AI in space should be in the future to provide solution and not just pixel to end user. Again, I repeat, a lot of very interesting things like super resolution, compression with AI, Data fusion don't make sense if we don't look at this future application. The combination of artificial intelligence, cloud computing, multi-sensor, tip and queue, autonomous satellites opens the market of low latency products. This it's the idea of receiving data from space while your satellite is basically overhead opens a huge market with great impact on sustainable development goals. In the same report from McKinsey, not only we're talking about 750 billion on the global economy, but we might eliminate, thanks to more efficient agriculture, 2 gigaton of greenhouse gas emissions. That makes 5% of the global emissions in 2030. Consider that your end users, when thinking about this algorithm, they don't have requirements, they have problems. So they're not aware of the solution that can exist thanks to this state-of-the-art AI application. From the other side, let me talk a bit ugly of my employer. One of the biggest hurdles for AI adoption are space agency. Our organizational structure are focused on low-risk mission, have difficulties in, as I said before, in understanding the problems of the end user. So most likely the stakeholders that will push for low latency service are not the ones serviced by the institutional space mission. And in general, this risk-averse structure makes the adoption of this new technology. Consider that 5 years ago, we were not talking about AI in space. Now, it has become all of a sudden a pressing issue. The life cycle of one of our mission is 15 years. So it's very difficult to insert this into our current life cycles. This is a showstopper in many cases. So in the sense, I'm very happy that you called me to talk. What the scientific community has to do is to increase the awareness of the fact that we have a lot of low-hanging fruits thanks to the very rapid evolution of AI application for image processing, and make the decision maker aware of that. With this, with very little overhead, I'm concluded. Gabriele, I hope I'm still within the times.
Yes, thank you very much, Luca, for this talk. It was very, very interesting. I think we have time for one short, quick question from the audience. Is there any question? Okay, if not, actually I have a small question for you, Gianluca. If you can tell us in 30 seconds, where do we stand in terms of qualification of components for deployment of AI on board?
For this point of view, I'll do two. There are two main roads, and they're all determined by the level of dependability you attach to your AI. If you are really cutting it with an axe, so a bit simplifying, if you have a platform applications, so applications that are safety critical for what you're doing, like robotics application in orbit servicing, in this case, you mostly have AI running on space qualified components. On the processor side, we are improving a lot because we will have, thanks to JPL microchip, we will have a new RISC-V multi-core with the AI vector acceleration available beginning of next year. And this will be the workforce for the future mission, like a Mars helicopter that now is flying a commercial off-the-shelf processor will have this processor. So is on the order of magnitude of performance of the old Qualcomm 603 flying now on in sight. On the payload, on the helicopter. On the payload side, we have now available high-end FPGAs, basically the Versal FPGA, but also something from Intel that can be used as bespoke accelerators for AI-driven processing application. The processes to develop an application purely in machine learning for space are not really qualified, and we have to move from formal qualification to functional qualification. So some of our standards need to be revised, but there are a lot of synergies of what's happening now, for example, in robotics or in self-driving cars. So there are hopes. Does this answer to your question, Gabriele?
Yes, absolutely. Thank you very much a lot for your talk, Gianluca.
You're welcome, Gabriele.
So, and now we have arrived to, I think, one of the most weighted part of this workshop. That's basically the award ceremony. And for this, I will leave the floor to Jamila.
Right, thank you for your patience. I hope you enjoyed all the talks and the posters. We will now announce the winners for both streams. So,
Drum roll.
yeah, drum roll for stream 1. So we have Rengan Lee. Help me with the pronunciation, TJ. Rengan Lee.
Rengan Lee, yeah.
Rengan Lee and co-authors from IEIT Systems. That's the first place for stream 1. Not sure, no paper. And I think they are not attending today, unfortunately, for visa reasons. So we'll send the award, the money, as well as the certificates to the authors. This is a second place for stream 1.
Qishuan Wang.
Qishuan Wang from China Academy of Information and Communications Technology on second place. So that's for stream 1, and the split is 700 and 300 euros. We thank our partner LMO for the prize. We have the CTO actually sitting here today. Thank you very much, Marcus Perez. We continue with stream 2. So we have the first place for Jianghong Zuo and co-authors from Nanjing University of Aeronautics and Astronautics and University of Chinese Academy of Sciences, Technology and Engineering Center for Space Utilization, Chinese Academy of Sciences. First place, that's amazing. That's the biggest challenge actually with the estimating trajectories. And we have the second place, Kun Liu from Nanjing University of Science and Technology. And we have a third place. There is no monetary award, but we will be sharing certificate as well with the group Yunfeng Tang. Is that good? Yeah. From Academy of Mathematics and Systems Science, Chinese Academy of Science, and MAIS, Institute of Automation, Chinese Academy of Science. Congratulations, and thank you for participating. And we look forward to the next edition. You can clap. I'd like to thank again the sponsor NMO, and also mention that there are openings in computer vision. So there are multiple openings for different seniority levels. This is based in Luxembourg, and the CTO is right here. So if you're looking for new positions, exciting positions in AI4Space, SSA, talk to him. Thank you.
Thank you, Jamila, for that very exciting result announcement for Spark. We also hopefully have another exciting session here for the paper awards. Unfortunately, we couldn't secure financial sponsorship for the main workshop, so unfortunately, no cash rewards are attached to the awards here. But hopefully, the glory of that is useful enough as a motivation to further work in this area. So without further ado, let's look a bit more into what awards are we looking at today. We're hoping we are awarding a Best Presentation Award, a Best Paper Award, Honorable Mention, and Best Paper Award. For the Best Paper Awards, the main one and the Honorable Mention, these were decided based on voting and evaluation by the workshop organizers. By this stage, of course, the organizers get to see who the authors are, and we have excluded from consideration papers with workshop organizers as authors, obviously. Not only we looked at the scores of the reviewing, but we also read the papers ourselves to make up our minds. So that's how the awards were decided. For the Best Presentation Award, unfortunately, we didn't have time to do that because we had to do that on the fly. So we will have to review this after the fact. So get ready for a message regarding this. After this session, we'll go back and huddle and say, which presentation were we all impressed by? So that will come later. Next up is Best Paper Award. Honorable mention goes to mitigating challenges of the space environment for onboard AI design overview for a recently launched payload, presented today by Jonathan Morgan. But it's a sizable team there with the first order Miguel Ortiz de Castillo. So congratulations to you. We will send you hard copy certificates. Sorry, we'll send you a certificate later. So the Best Paper Award goes to Revisiting the Domain Gap Issue in Non-Cooperative Spacecraft Pose Tracking, authored by Kun Liu and Yongjun Yu. Congratulations to the authors. Kun Liu, are you online? Kun, are you online? Are you on Zoom?
Yes, yes.
Congratulations. We will send you these later. Well done. Okay, so we're almost at the end of this workshop. Just a few parting remarks, shameless plugs for colleagues. As Gianluca mentioned, we as researchers, in order to grow this field, need to convince stakeholders in industry, in government. What we can do as researchers is to build momentum in research, and we do that well through organizing. One of the ways that we do that is by organizing events such as this one and bigger ones that you see here on the list that we think are relevant, that, in my personal mental awareness are on the horizon. There are, of course, others. They might have slipped my mind yesterday. But here are some of the upcoming ones, also concurrent ones. iSparrow International Space Robotics Conference just completed not long ago. The next one in 2025 could be happening. talk to Sunjo about it.
Maybe happening.
Maybe happening at Caltech. So watch that space. So the one that's concurrently happening now, approximately concurrently happening, is SPAICE. I was told it's pronounced SPICE. Paper decisions are being made at the moment, and that's organized by ESA. ICIRIS is, as you can see here in this poster, in this ad, is still accepting submissions, and its abstracts due 23rd of June. And the main organizer, Jonathan Ralston, said, if you need an extension beyond 23rd June, contact him. I can quote him on that. He sent me an email. So, if you want more AI4Space, that could be the next venue you look for. And further down the horizon, if this workshop is of interest, I think there are some encouraging signs today, maybe AI4Space Workshop 2025. And we welcome colleagues to come and help us organize the next edition. So with that, thank you very much from the organizers for your support. Hope to see you continue working in this very interesting area, and enjoy the rest of CVPR and Seattle. See you around. So yesterday. Yeah, yes, because that's so like oh,